Oh, you're gonna go to Kenya? Yeah, I need to. Oh. I need to turn in my time sheet today, so I'll go with you.
Okay, so let's continue where we left off, chapter 19. So we've got the heat into a gas is changing the internal energy of gas plus the work done by gas. We have the first law of thermal. And remember, it came in different forms, but this is the one that I'm primarily going to use. If you put in heat, the gas can do work, and the internal energy of the gas can increase. And then we talked about isobaric process, where the pressure is constant. And we said that the heat into a gas is going to be delta E of gas plus work by gas, which is PdV. Actually, before isobaric, it's probably better to review isovolumic because that's a bit simpler. Isovolumic is the volume is constant, right? So in that case, we have the volume is constant. The heat into the gas is the change in internal energy of the gas, and the gas doesn't do any work. So then you have Q is delta E of gas, and then we let that equal to N, number of moles, times the molar specific heat at constant volume, times change in temperature. So this one is similar to what we did for liquids and solids, where we said mass times C. We said Q is equal to MC delta T, or H is MC delta T. So the main difference is we're changing it to N. Instead of mass, we're calling it moles. We're changing the C into molar specific heat. And then we're putting the subscript there. Why? Because for gases, their specific heats at constant volume are different than their specific heats at constant pressure. For solids and liquids, they're about the same. Constant volume, constant pressure, because solids and liquids don't expand a lot anyway. So their CV and CP are about the same, so we don't need to distinguish the CV and CP. We can just say C. See, that's the main idea. So with liquids and gases, with liquids and solids, we have just C. And the other difference is that with liquids and solids, we use their masses more. You see? With gases, we use N, and then we differentiate between CV and CP. Okay? So this is molar specific heat at constant volume. Then we go to isobaric, and then we say Q into gas. Delta E is NCV delta T plus PdV, where the pressure is held constant. Okay, so then you use the PV is nRT, so PdV, right? If I take the derivative of this, but remembering that P is constant, PdV is just going to be nRdt. So this is just simply going to be nRdt. And then I can add these two. Q into gas is NCV plus R dt. And then CV plus R I define as I define that as CP, the molar specific heat at constant pressure. So we said that it's harder to heat a gas at constant pressure because when you're putting heat into it, part of the heat is going into the gas doing work on its surrounding. So not all the heat is going into the changing its internal energy. So it's harder to heat the gas at constant pressure. For liquids and solids, it doesn't matter because the increase in volume and their increase in length is negligible, you see. Even though their solids and liquids do expand very infinitesimally, you see. So now Cp is gonna be Cv plus R.
So you're saying that gases expand at a wider?
Oh, much, much more. Yeah, that's why when we say isovolumic versus isobaric, we have to contrast. How are we heating this gas? Are we allowing the gas to expand as we're heating it? If we are, the gas can expand a lot. Imagine I heat this room right now, put the heater on, and close the doors, the gas cannot expand. How is this temperature gonna change? Versus open the door and heat the room. You see? Open the door, heat the room, what's gonna happen? As the gas is heating, the gas is gonna expand. Well, that's a bit different. The open the door concept is a bit different because not only is the gas gonna expand into the outside, the gas from the outside is gonna come in, there's gonna be some interchange. So my example is not perfect example. I meant to say more something like heat a chamber where the chamber can expand. So I'll show you that in a second. Okay, the other concept that we talked a lot about is Cv for monatomic gases, Cp for monatomic gases. So that idea, Cv for monatomic was 3/2 R monatomic. And then Cp, of course, is just gonna be Cv plus R, so it's gonna be 5/2 R. And then for diatomic, Cv is 5/2 R. Cp is always 1 R bigger than that. So it's gonna be 7/2 R. So this is diatomic. And then polyatomic, Cv is 7/2 R, or depending on how many degrees of freedom there are, it might be 3 R. Cp might be, if it's 7/2 R, it's gonna be 9/2 R. If it's a 3 R, it's just gonna be 4 R. So this is polyatomic. And that's kind of where we left off at that. Let me take this opportunity to reintroduce, if you remember in Physics 101 last semester, there was a couple of websites that I went back and I used them besides Wikipedia, because this semester so far I've been doing Wikipedia and maybe some other websites, but I haven't gone back to those websites. There's a couple of websites that I used last semester quite a bit. So let me remind you of those. So you can always put this on your not playlist, but like history, and kind of use them as go-to websites. One of them is hyperphysics. If you Google hyperphysics, you could easily find it. And I like the way that they have the topics laid out, and it's like almost like circles, Venn diagrams. So they're saying this is all the fields of physics. So last semester, of course, we were concentrating on mechanics. This semester, it's gonna be heat and thermal and electricity and magnetism. And then the rest of this is Physics 103, waves and modern physics and relativity and quantum and all that. So, so then once you click on a certain topic, let's say heat and thermal, then it shows you the breakdown of that. I like this because it also shows you a little bit visual, because I'm also a very, very visual learner. When I see things like this laid out, it really helps me see the connection of everything that I'm learning so far and how they are tied to each other. Like internal energy, heat, system, first law of thermal, temperature scales. Well, that's what we started the semester with, right? Temperature scales, thermal expansion, then specific heat, enthalpy, phase changes, thermal equilibrium, zeroth law of thermodynamics. Where's my favorite ruler? Is it gone? I like pointing it with that ruler. Why did they take it out of here? My pointing stick. So then I have, so we've talked about specific heat transfer, conduction. You see, so the topic that we did with conduction kind of falls under the idea of heat transfer, convection, radiation. And then we didn't do relative humidity, but that's part of that, goes in there. And then the heat engines, isothermal, adiabatic. So we're kind of on this wing of it right now. Isothermal, adiabatic, constant volume. And then Wednesday we'll start the other wing, second law of thermoentropy. And then kinetic theory of gases, we've done that. Ideal gas law, equipartition of energy, we've done that, where the energy breaks into 3 degrees of freedom we talked about, right? And then Boltzmann's distribution, we've talked about that. So even though we had the test 1 today, never have the idea, oh, okay, test 1 is done, my learning has stopped, oh, I did bad on the test and that's it, you know. You always want to say that the test is like a learning tool. Oh, okay, maybe I got 20% on the test. Well, now I've got 80% to learn. Your learning continues. I know we've got to worry about the second test coming up, but in the meantime, what you should also do is leave some time to go back to previous materials while they're still kind of fresh in your mind, and review them and build up those skills, because all of this comes back on the final. A lot of people, what they do is they go on to the material of, let's say, the next test, and then they do that, they keep doing that without reviewing. And so now when the final comes, they've got a lot more work ahead of them. Now they've got to go back and review all the stuff they didn't understand on test 1, test 2, you know, and now all that, imagine doing that last week of classes. Doesn't work. So if you feel like the conduction was your weakest part, or radiation, you can use this website, go to that, and then you can, let's say radiation. So E sigma A T to the 4th. And they have problems there. So you can say, oh, okay, you can put in the temperature of the cold, the temperature of the hot, calculate stuff. And they start with easy problems. You can put it in, you do the calculation, and you get, so I like this website because it's laid out nicely, and they have very easy problems for you to build confidence in that area. And then you can kind of, there's also a lot of places to click to go to some other, so if you click here, modeling of cooling time, dE/dt, that's the kind of problems we did where we said, oh, how long does it take to reach a certain final temperature? Oh, you see that? You integrate T hot to T final, 1 over T to the 4th, right? And then you could keep, you know, you could keep going down the trail that it takes you, modeling the radiated cooling of a volcanic fragment. So, you know, what happens might be that you might be interested in that topic, and you learn more about it, and then it takes you down that trail. Or you might say, well, you know what, I think I really get it, so I don't need to do more. And here again, some more problems, practice problems for you to try. You know, so then you just say, go back. So now for now, we are on this topic, isothermal. Okay, so isothermal we haven't done yet. I'm gonna start that now. Let's see here. adiabatic. Adiabatic process depends on, before actually starting the concept of adiabatic process, I want to explain this idea of gamma. Gamma, the ratio of specific heats. So since we've already talked about CV and CP, the ratio of CP to CV has interesting applications to gases, and that's known as the gamma factor. Gamma is defined as CP to CV, and of course it would be unitless, right? Unitless. So for monatomic gases, what would that be? 5 halves R over 3 halves R. R cancel, 2 cancels, 5/3, which is 1.6, 2/3, 1.667. So in other words, it's 1.66. You could almost kind of think of it this way, maybe word it this way. Since the ratio of the two is 5/3, you could say 166.7%. So it is 166.7% harder to heat a gas isobarically versus isothermally. No, not isothermally, versus isovolumically. So in other words, you have, let's see, delta Q into a gas is NCV delta T, right? This is isovolumic. And then Q into gas, NCP delta T, isobaric. So if this is larger than this by a ratio of 1.667, what would that mean? For a given amount of heat flow, the temperature, the change in temperature of that gas is going to be less, right? If this is bigger, the change in temperature is going to be less for an isobaric process. So you could say for a monatomic gas, it is 166.7% harder to heat it, we can say, to heat it isobarically versus isovolumically. Does that make sense? Because this is isobaric. So if this is larger by 1.667, then this is less by that same ratio. So it's, of course, it's harder to heat it because for the same amount of heat flow, the change in temperature is less. Okay, but how about diatomic? For diatomic, what's the gamma? Then you do 7 halves R over 5 halves R. .4. So it's the ratio of 7 over 5, right? 1.40. So then what would you say? For a diatomic gas, it is 140% harder. For diatomic, it is 140% harder to heat it isobarically. So in other words, what's happening is as the complexity of the molecule is getting more complex, what's going to happen when I go to polyatomic? Gamma is going to be the 9 halves R over 7 halves R. R cancels. 9/7, which is 1 and 2/7, so that's 1.28 about. So then for polyatomic, it is 128% harder. So this is, maybe we could do kind of like graphic. Maybe you could do like a graphical interpretation of this. You can say, let's say you have 1 mole of an ideal gas, and you want a change in temperature of 1 Celsius. How many joules of heat should I put into it so that its temperature increases by 1 Celsius, if it is a monatomic gas? So if monatomic, how many joules to increase it by 1 Celsius? If monatomic, how many joules to increase by 1 Celsius isovolumically? So there's 2 things that, in other words, there's 2 factors we can change here. Whether we're trying to increase the temperature isovolumically, or are we trying to increase it isobarically? And the other factor we can change is whether or not the gas is monatomic or diatomic. You see? So let's keep it, for example, let's keep it monatomic and say how many joules to increase it. So then we just use the equation Q. If there's 1 mole and delta T is 1, so then Q is just going to be whatever CV is, right? And then CV is 3 halves R, and then R is 8.314. So then that's going to be how many joules of heat I should put in to increase the temperature of 1 mole of a monatomic gas.
Where'd you get the 8.314?
That's the value of R, the gas constant. 12.47 joules. So we could say, let's say, Q, so monatomic, so it'd be like, let's say, 12.47 joules. Now, if I did diatomic, how many joules to increase by 1 Celsius? How many joules to increase by 1 Celsius isovolumically? So I'm trying to keep it isovolumic, but just increase, right? So monatomic, so diatomic is going to be what? Then it'll just be 5 halves R. Right, so then that's going to be 20.79 joules, right? So then if I graphed it, the diatomic, so something like this. And then polyatomic is going to be what? 7 halves R, right? Let's say I've used the 7 halves R, so it'll be 3.5 times 8.314, 29 joules, right? So MdP so as I increase the degrees of freedom that the gas has, remember monatomic has 3 degrees of freedom, diatomic 5 degrees, so this is like 3, 5, and then this is 7 degrees of freedom, right? So then it becomes harder to heat that gas. Now let's make another graph for isobaric, you see? So how hard would it be to increase the 1 mole of gas monatomic isobarically, right? So isobaric would be the 5 halves R, right? It would be the same because see here, the isobaric of the monatomic is the same as the isovolumic of the diatomic, you see? So on the graph, this would be like here. If that's 20.47. So this is the isobaric of the monatomic is the same as the am I saying that right? Yeah, isobaric of the monatomic is the same as the isovolumic of the diatomic, right? This graph, I'm getting my little tongue twisted too. So this is isovolumic, okay? So then, how about this guy, diatomic? What was this value for the last one? That was 29, right? So the gaps between them should be uniform because they should be increasing by R, you see? I like this graphical interpretation. I think this is the first time that this has come to me. It's a eureka moment. Don't worry, I'm not about to run naked around ELAC. So 29 joules, right? So the gap between these is just the equivalent, R, R, you see? This is R and then another R, you see? So now, so this is isobarically. How about diatomic isobarically? And the diatomic isobarically is the same as the polyatomic isovolumically. So then the diatomic goes over here. So basically, is the gap between them the same? Or are they getting close? No, actually, I should draw them so that the gap is still, if this is 20, and this is R, and this is 20, this is 29, so that actually the gap is uniform. You see, the gap is uniform. How about the isobarically for polyatomic? Then that's going to be 9 halves R. So isobarically is always constantly 8 joules harder to heat for that 1 mole of gas. 8.314 joules hotter. But now, take the ratio of this to this. Take the ratio of this to this. Not their difference, but their ratio. In other words, if I'm 0 years old, I'm born, and I have a brother that's 8 years older than me. That's the value of the gas constant, right? My difference between our ages is 8. The ratio of his age to mine is infinity, 8 over 0. He's infinitely older than me, all right? So what's going to happen to that ratio? As he becomes 10, I become 2. He's five times older than me. You see? And then when I become 12, he becomes 20. He's what? 1 point something older than me. He can still beat me up quite a bit, but when I turn 20 and he's 28, I could do some damage to him, right? Our ages are getting closer together, not age-wise, ratio-wise. You see? So this to this, and that's what's happening to gamma. It's not that when you get into polyatomic, it's not that it's easier to heat it, but it's just that it's easier to heat it in comparison to isovolumic. Isobaric is not that much harder to heat anymore. It's the ages coming, not that the ages are coming closer together, but the ratio of the ages is coming closer. You remember these kind of problems in pre-algebra or algebra probably. Like if you are 8 years older than your sister now, and 10 years later you're going to be twice as old. What is your age? Do you remember this kind of problems in math? No? Mm-hmm. Yeah, that's the kind of things. So I always like to tie that. So that's what it means to say gamma, the ratio, as you're getting more complex, as the molecule is getting more complex, the gamma is getting closer to 1 because the two of them are increasing. It's getting harder to heat, but isobaric versus isovolumic isn't making that much difference anymore. Whereas monatomic, gas is almost no complexity. The energy you put in isovolumically goes into the motion. Isobarically, it's harder by a value of R. So isobarically, the gas expands. Because a lot of its energy, for monatomic, because a lot of its energy is not tied to the motion of the object, the vibration, it's just translation. When you allow it to expand, it becomes a lot harder to heat because the gas expands. In other words, not a lot of its energy is tied to its translational motion. To its vibration, because it doesn't have vibration, you see. So in other words, it's noticeably harder to heat it isobarically versus isovolumically. So this concept of gamma, as you can see here, it says the ratio of the specific heat Cp to Cv is a factor. So it becomes a factor in other concepts too, such as determining the speed of sound in a gas. So the speed of sound is a topic that if you took physics 2 with me, we talked about that. And if you haven't, when you take physics 103 and you talk about waves, you're going to talk about the speed of sound. The speed of sound in air is something like this. 331.4 times square root of 1 plus T over 273. This is usually the equation we teach people, where temperature T is measured in Celsius. And you could also measure it in Kelvin, 331.4 square root of 273 plus T over 273. And then 273 plus T is Kelvin temperature. Temperature in Kelvin. So this is the equation that we usually teach for the speed of sound in air. So if you click here, it takes you to the link that I said, where it takes you to some other site inside of their website. So it says the speed of sound in an ideal gas is given by the relationship square root of gamma RT over M. Kind of almost resembles the equation for the root mean square velocity, right? Remember what was that? So I'm kind of going on maybe a 5-minute tangent, because it's an interesting topic. Wasn't it 3 RT over m? The root mean square velocity of a gas, of the gas molecules. This equation is for how fast a sound moves through that gas, sound wave. So how does a sound wave move? Well, the molecules have to propagate, right? And then a sound pressure has to be created here, and that pressure variation has to transfer high pressure, low pressure, high pressure, low pressure, and then that pressure has to transfer from one area to another, and then that's the velocity of propagation of the sound wave. You see? So the velocity of the sound is going to be square root of gamma RT over m, where gamma happens to be the ratio of Cp to Cv. You see? So which one is faster? The velocity, the root mean square velocity of the molecules, are they moving faster? Or the gamma moving faster? Well, logically, which one do you think should move faster? If people are moving, let's say a bunch of people are moving, right? Like this, bunch of people are moving, and then there happens to be a disturbance at one end, right? Which, let's say the disturbance happens to be like a car that's kind of coming this way, a presidential car. Today there's a presidential debate thing, the lady who's running for president. So imagine you're in the street, a bunch of people, and then presidential car is coming, right? And then you're walking. Oh, so you notice a car is coming, you start slightly shifting the direction of your motion that way, away from the car. So now I'm moving, so slightly this way, but another molecule is coming this way, this way, this way, right? So that information of me trying to get out of the way of that car, it's gonna take a while to trickle its way down, right? So you can kind of say that this should go a little slower than that. The velocity of the molecule should be slightly faster. Well, what is gamma? Well, most of the time it's about 1.4, 1.2, what was for monatomic, what was it? 1.67. So even monatomic, which is the largest gamma, it's still gonna be less than 3. So therefore, velocity of sound is slower than the velocity of the molecules. You see? Gamma RT. So here what they're doing is, for air, gamma is 1.4. So therefore, air is what kind of molecule? Just by knowing it's gamma, do we know what kind of molecule? Diatomic, monatomic, or polyatomic? Diatomic. What is air anyway? Mainly nitrogen and oxygen. 70% something, 70 something percent nitrogen, and something like 20 something percent oxygen. What are those two molecules? And nitrogen is N2, right? And then oxygen is O2. Both are diatomic. So yeah, I'm not surprised that air is 1.4. So if I want to know the speed of sound in air, 1.4, 8.314 over the molecular mass of air. What are they using for that? 28.95, because you probably have to take a percentage. What percentage of air is oxygen? What percentage of the air is nitrogen? And then kind of come up with an average molecular mass of air. So 28.95 grams per mole. Times T. Now if you just calculate this part, it gives you 20.05. Square root of T. Well, it happens to be the same thing that we teach in Physics 103, but over there we don't talk about the gamma a lot. We just give them the equation, because whoever has taken that class probably hasn't taken 102, right? So now you guys are kind of trying to learn both. So over there we do this. So if you take 331 divided by square root of square root of 273 and square root of tk, this divided by this should be 20.1. $331.4 divided by 273 square root. Yep, 20.05. But which one is more fundamental? This equation more fundamental or this one? It's this one. This one is derived from this. And so this is more fundamental because I could put any gamma, any molecular mass. This one doesn't have the molecular mass in there. So it only applies for air. This one I could put the molecular mass of any element. And I could put the gamma of that element. So it's more fundamental. For helium, gamma is 5/3. What kind of gas is helium? It's just He, I think, monatomic. So what would its gamma be? Ratio of 5 to 3. So even if you forgot, just go this to this. 7 over 5 is 1.4. 5 over 3 is 1.67, right? So the gamma would be 5/3, and the molecular mass is 0.004. So its speed of sound at the same temperature is what? What is the velocity of sound at the same temperature? By what temperature do they mean?
20 degrees.
Oh, at 20 degrees Celsius. So how would we calculate that? Let's do it and see if our answer is right. For the gamma, we would go 5/3. R is 8.314. What would I put for the temperature? 20 degrees Celsius, right? So that's 293.15. What's the molecular mass of helium? 0.004. I could just use 1.67 for the gamma. 1.67 times 8.314 times 293.15 divided by 0.004 square root. No, I did something wrong. What'd you get?
1007.73.
1007.73 meters per second. So sound wave travels in helium a lot faster. Well, the root mean square of helium is also going to be more too. It's going to be 3 RT. So that, and then the mass of helium is 0.004, right? So yeah, helium molecules are moving faster, and therefore they should permit sound to travel faster. That's why when you inhale helium, your voice goes up. The frequency of the standing waves created in a pipe, or an open pipe, right, depends on the velocity of the sound in that pipe. If the velocity goes up, the frequency goes up. So when you inhale a helium balloon, the standing waves that are created in your trachea, the frequency goes way up because the velocity goes up. So let's try that here. If I put velocity of sound in helium, what am I supposed to put? What'd you get? 100,000? 4? I'm not sure what I was supposed to put here. Doing this calculation for air gives you 331. So velocity of sound in the air is 331.4 plus 0.6 t. Or they're giving another version of this equation. 331.4 square root of t. Oh, but now they're changing that to temperature in Celsius. How did they change that equation to that? 31.4. Oh. They went back to the original equation. And they said 331.4, 1 plus T over 273 to the 1/2 power. They did a Taylor series expansion of this.
Can you show
Trying
us?
to catch us off guard, huh? 331.4, 1 plus T over 0.6. Yeah, okay, so. Okay, I think that's it. So that kind of gives you an idea that this gamma concept, the ratio of Cp to Cv, is not only important in this scenario, but in other things such as speed of sound. Gamma. So if we go more in detail, what's going to happen? Gamma of H2. What's H2? A diatomic gas, right? Diatomic gas. So if the hydrogen is very cold at negative 181, they're saying the gamma is 1.6. Also, it's behaving more like a monatomic. You know why? Because it's so cold that its vibrational energy is negligible, only translational. It's acting as it's a monatomic gas. So that's why I need the pointer, 1.6. Now you make it warmer, gamma goes down, 1.45. So that means the gamma doesn't have to jump in increments. It could kind of gradually change, you know, to 1.45. Then you make it room temperature, 1.4, 1.41. Okay, so now it really, the diatomic nature kicks in at 20 degrees Celsius. You see why? So it's pretty complex. You go to 100, it's going more down, 400 Celsius, more down, 1,000, 2,000 Celsius, 1.31. So 1.31, it's almost acting polyatomic. So even though it's diatomic, more forms of energy are coming in as you're heating it. Maybe vibrational energy. The two hydrogen molecules are vibrating this way, not just rotating this way and this way, you know. So gamma is changing as you're heating up. So of course in our problems, unless otherwise is stated, we're gonna assume if it's a H2, that it's kind of like maybe room temperature, and we're just gonna say, okay, if it's diatomic, it's 1.4, you know. Unless the problem tells you, oh, okay, the gamma is 1.35 or 1.31. Okay, helium, they only gave you the temperature at 20, 1.66. Well, that's standard monatomic, 1.67, 5/3. H2O, water vapor molecule. So 20 Celsius, 1.33, 1.32, 1.31. Well, it doesn't change much. So it's more like polyatomic, 1.28, right? 1.28. So water vapor more or less stays this equivalent nature. Argon should be, see when it's really cold again, it's the gamma is higher, but when it's room temperature, fully monatomic. You see, dry air, more or less diatomic. You see, so I kind of like seeing that kind of stuff. Carbon dioxide 1.3, 1.3. Okay, pretty much polyatomic, but you can see it does change 1.28, 1.23, and then by the time you go to 1,000, more things are happening. The gamma is way down, and then so on and so forth. So you can kind of see like that. Okay, so now that we've got that covered, we can say, let's go to isothermal processes. What's an isothermal process? Well, the word iso means same, thermal means temperature. That means you're not actually heating the gas, you're allowing the gas to, you're heating the gas, but you're not allowing the temperature to change. That means you're heating the gas, you're allowing the gas to expand, but its temperature should stay constant. You see, it's kind of hard to do, but it's kind of doable if you try hard. Oh, in the lab we had an isothermal, right? Remember when we put the can in a cold bucket of ice water and the hot water? That's kind of isothermal, yeah. Isothermal. So Q into gas, delta E of gas plus work done by gas. Well, delta E of gas is 0 in isothermal because temperature is constant. So then you get Q into gas is work by gas. Well, what does the PD diagram look like? V1, P1. Right? So if we have P1, V1 is equal to nR T1. So the gas at this corner, the gas has temperature T1. So if the temperature is constant, that means the temperature of the gas is gonna always stay T1. But as the volume increases, the pressure is gonna drop, right? So the pressure is equal to nR T1, which is constant, divided by V. So it's a y equals 1 over x graph, like this. Y equals 1 over x. So it goes like this until you get to V2. You see? So then P2 is going to be what? P2 is going to be nR T1 over V2. But then you can say nR T1 is also P1 V1. Which one is this one called? I always get confused. Charles's law, Guy-Lussac law, and Boyle's law. I never learned the difference between all of those three. I always have to wiki it. But it's one or the other. One of them is pressure constant, one of them is temperature constant, one of them is volume constant, right? So, okay, so then what's the work done by the gas? It's gonna be the area under this graph. So how do we do that?
I agree.
Because the pressure, as you're going like this, the pressure is changing, right? So the work is equal to the integral of P dV, right? But P is not constant. So what's the equation for P and in terms of V? P is going to be nRT1 over V. You see? nRT1 over V. From V1 to V2. So therefore, the work done by the gas is going to be ln of V2 over V1. Let's see if that's what they have. That's what they have, you see that? nRT, the work done by the gas, ln of V final over V initial. Could we also write it as T final over T initial? No, I mean P final over P initial. Can I replace this? P final over P initial?
No, P initial or P final?
Or is it P initial over P final, right? Let's see here. If I'm gonna do V2 over V1,
No.
reciprocate P2 over P1, it's gonna be P1 over P2, right? Yeah, okay, so then it should be the other way around. P initial over P final. Yeah. The ratio of V2 to V1 is the same as the ratio of P1 to P2. Because when one drops, the other one goes up, right? So they integrate that. This one, the calculation is not too bad. The other website that I could show also is this one. These are simulations. One is called PET, PhD, University of Colorado Boulder. And these are the topics, and these are all simulations, computer simulated problems and situations that you could play around with. And then these are the topics. The other one is physics Wolfram. This is a lot more advanced. Wolfram demonstration project. There's a one for physics Wolfram. There's calculus Wolfram. There are all simulated ones. So if we look at this one, this one has a lot more simulations and almost goes beyond the scope of this course. Some of the problems are way apart. Let's see, for this one we can go to thermal. I already looked at some of them. Oh, is this the one? It's an interactive simulation that you could go out like this, put in some gas molecules. As I put in gas molecules, what's happening to the pressure? 30.8 atmospheres. I could choose a different molecule. Oh. See, of course, the lighter ones should be traveling faster at the same temperature. Did they tell us the temperature? 300 Kelvin. So then I could put in heat. Pressure is going up. But this is isovolumic, right? Volume is not changing. I could change the volume. Oh, you can even count the number of particles there are there. It's quite a bit, but let's see here. Release some of the gas. It's cool. It's cool. I want to see if I could do one where. See, hold constant, nothing, volume, temperature, pressure. I don't know what they mean by PV, PT. So if I want to hold the temperature constant as I pour in heat, what's this one? Bucket?
Well, you're holding the temperature constant, right? You can't add more temperature.
Oh, well, no, I could heat it, and then I could heat it, but the heat that I do goes into it, increasing the volume. So, what is this? Temperature cannot be held constant when the container is empty. Oh, there you go. Let's go temperature constant. Oh, as soon as I do temperature constant, how about pressure constant? Pressure, temperature. Pressure, volume. Okay, in that case, I'm putting in heat. Okay, pressure, volume. So I'm putting in heat. And the temperature is going up, you see up there, and the pressure is being held constant. Oh, nice. So if we had time, we could explore that one more. In the other one, since this one includes a lot of demos, probably it's best to just do like a search. Let's say I wanted to do isothermal expansion. So you could do any topic by search. Reversible expansion and process. Reversible and irreversible expansion of compression, or reversible and irreversible isothermal expansion of an ideal gas. Then you say download to the desktop. This is the Wolfram one. So we're gonna do reversible process. In other words, we're gonna assume that there's no frictional losses, energy loss to friction. So you do the number of moles. The 8 moles is the most. Temperature is 373 Kelvin. Initial volume. So reversible isothermal expansion. So how much work is the gas is gonna do? So we have in our case, we have 8 moles of gas. By the way, for isothermal, notice the topic of CP/CV didn't come in. It was just NRT, LNV final over the initial. So the work that you do, it doesn't matter Oh, because all the work you do goes into changing the gas doing work, it doesn't matter if the gas is also vibrating, you see? What matters is it's doing work against the surrounding. So that's why the vibrational energy didn't matter, because the temperature is not changing anyway. So it's just nRT ln final over the initial. Okay, so the initial temperature is 373. Actually, the temperature is gonna stay 373, which is 100 Celsius, right? And then the initial volume is 17.4 liters. And then the final volume is 7 liters. So the PV diagram will be, let's see, temperature, no, I mean volume here. So this is 17.4, 70. So what would be the work done by the gas? Then we can just do nRT ln the final over the initial. 8 times, this is 8 moles, 8.314 times 373 times the final. Do I have to change to cubic meters? Not for these purposes, because if it's a ratio, the ratio of liters to liters is the same as the ratio of their cubic meters. So that would be okay. So I can just keep it in liters. So that's the work done by the gas in that problem. This is, we can say this is part A. And then you get used to writing the works, because a lot of times it's gonna be big numbers, so you can write them as a kilojoule. So it's gonna be 34.53 kilojoules. Is that what they have? So then you can check your answer with the app. They sure did very small. They did negative 34 kilojoules, negative 34. So they're doing the work done on the gas, which is negative 34, but it's better. In this case, I'd rather just say the gas is doing positive work rather than I'm doing negative work. So it's better just to write as positive. So then they're saying if it's an irreversible process, the gas is gonna do less work because some of it's gonna be lost to maybe friction or something, but don't worry about that. What else can this problem ask? Well, it can ask for what is the initial pressure, what is the final pressure, so we could answer that. What's the initial pressure? So then you do nRT1, no, divided by V1, right?
Professor, you got a negative number for that word.
No, 70 over 17 should be positive.
Oh, that's 17?
Yeah.
Oh, I got, oh. Okay.
Yeah. So then you're gonna have 8 moles, 8.314, 373 for the temperature, right? And then the volume, now I'm gonna change it. It's 17.4 liters. So then what's the conversion between liters to meter cubed?
Meter cube, 10 to the
1,000 liters is 1 meter cubed. 1,000 liters is 1 meter cubed. 1 meter cubed is a big volume because imagine it's a meter by a meter by a meter. So it's almost like these huge boxes that you ship to some other country to your relatives or something, you know, it's a huge. So 1,000 liters is a meter cubed. So then you say 1,000 liters is 1 meter cubed. Okay, then that's gonna be the pressure.
Mega.
1,425.8 kilopascals. Right, is that high pressure? Oh yeah, because 1 atmospheric pressure is 101.3 kilopascals. Right, 1,425, that's almost like 10, 15 times atmospheric pressure. So it's like 15 atmospheres. Humongous pressure.
Can you go, so you said you didn't do convert it to meters cubed the first one because it was just a ratio?
It's a ratio, yeah.
And then for the other one you did because?
Because I want to know the absolute pressure of P1. So then convert. Unless I use the other version of R, which is 0.08214, I think. Then I could use, then I could just use 17.4. No, wait, is that right? 1,000 liters. Yeah, then I could just use 0. Moles, liters, atmospheres. Oh yeah.
But,
If I use that,
yeah.
if I use that way of
Yes.
doing it, 0.08214, then the answer that I get for P1 will be in atmospheres, right?
Yes.
Yeah, okay.
Oh.
So now I'm getting it in kilopascals. Okay, for most part, I prefer kilopascals because if we need to get the work under there, pascals times meter cube gives you joules. So we prefer that in physics usually more often. So that's why I use this one. So I'd rather convert the liter to meter cube. Okay, the last thing is P2, NR T1 over V2. Well, you know what? I don't need to redo it because it's a ratio thing, right? Because in this case, the temperature is staying constant. So all I can say is forget this way of doing it. I can say P2 to P1 is the same as V1 to V2. You see? So then if this one is 1,425.8 kilopascal, then V1 is gonna be, actually that one I could just keep it in liters since it's a ratio, right? Then I can say 70 liters over 17.4 liters, right?
Yes.
70 divided by 17.4. No, something is wrong. The pressure should be dropping.
It drops.
17.4 over 70?
I think I did something wrong. Let's see, PV is constant. It's PV is constant. So it's P1, V1 is P2, V2.
Okay, you're right.
P2 over P1 is V1. No, it's right. V1. Oh, hold on. V1 is 17.4.
Yeah.
V1 is 17.4 liters over 70 liters. Yeah, it's the other way around. Because the pressure I know should be dropping. That's why, again, doing a picture is important so you can see, oh, okay, I'm expecting a drop in pressure. So 17.4 divided by 70 times 1425.8. 354 kilopascals. Well, now we're down to more regular pressures. 354.4 kilopascal. So you see, I did that problem with some numbers and I'm getting the same thing. But now we can go one more step. Let's make it a complete cycle. So let's say the gas is taken through 3 processes. Isothermally expanding, isobarically compressing, and then isovolumically going back up to the original state. This is called a complete cycle. What's the total work done by that engine? So now we've made an engine out of that gas.
You said went to ISO.
Isothermal, isobaric, isovolumic. When you do a complete cycle, you created an engine. That's the idea of how steam engines first came about. Is we run an engine through a cycle, and we have that engine do some kind of work. And this PV diagram revolutionized the world. The Industrial Revolution came about because of this, right? So steam engines, trains, locomotives, all that stuff. Okay, so now if I go back isobarically, the gas is gonna do negative work. I'm gonna be doing, in other words, I'm gonna be compressing it. I'm doing positive work, but the gas is doing negative work. You see? So then what can we ask for that portion of the stage? What can I ask? Well, I already know the volume that it's going to. I know the pressure, so I don't need to ask that. How about the temperature here? Can I ask that? We can call that T3. This one is T2, but T2 is the same as T1, since this is isothermal. This is T3. Okay, I could ask that because T3 is gonna be colder, I think. Hold on. As I compress it. As I compress the gas. No, as I compress the gas, it should heat up, right? T3 should be warmer than it is here. Wait, what was the temperature here? I never wrote it down. 373, right? 373. Here the temperature is also 373. Yeah, I believe it should warm up, right? If I go down. So then how could I find that temperature? It's a pressure is constant, so what's the governing equation? PV is nRT. So if that's constant and number of moles is constant, the gas constant is constant, so we're just gonna say V is proportional to T. In other words, you look at the process that you're doing, you're saying, this is constant, this is constant, this is constant, so V is linearly proportional to T. So then you're saying V2 to V3 is gonna equal T2 to T3. Call this V3. Right? You see? So then it just is a simple ratio. So then the V2 is gonna be 70. V3 is gonna be the same thing as V1, 17.4. T2 is gonna be the 373. And T3, no, it looks like it's gonna be colder, I'm wrong. Because I said, if I compress it, it should heat up. Oh, you know why? Because heat is escaped. It's not that easy. You can't say when you compress a gas, it should always heat up. It depends what else is happening as you're compressing it. If you compress it and heat is escaping, then it could cool. It looks like it's cooling. You see, T3. Okay, so what is that?
So,
1,500. Wait.
what?
Yes. I keep getting wrong answers. 373 times 17.4 divided by 70. Oh no, 92 Kelvin. Oh wow, it's really cold. 92 Kelvin. The gas is just going to turn into liquid by that point. The phase transition might happen. It's like really cold. So 92 Kelvin it will reach here. Okay, now what's the work done by the gas? The area under the graph, right? Under the isobaric portion. Work by gas. In that isobaric, what is that? P delta V, right? Negative P delta V. I know it's going to be negative work because I'm the one compressing the gas, you see? So the gas is being compressed, so it's doing negative work, I'm doing positive work. So what's P? At the pressure 354.8 kilopascals, right? So negative 354.8 times 10 to the third pascals. What's the change in volume? Now I should do it in meters cubed, right? The change in volume is 70 minus 17.4, but that's liters. And then 1,000 liters is 1 meter cubed. And then this 1,000 cancels the 10 to the third from the kilo. So then you just subtract the liters and you multiply by 354.
Wait, what?
See, right now, what you guys, this topic that you're doing is full-on thermal with thermodynamics, where what we were doing back then was just pseudo-thermal. 70 minus 17.4 times 354.8. So the gas does negative 18.67 kilojoules of work. Work by gas. Now you might say, the student is going to say, hey, delta V, shouldn't delta V be the V final minus V initial? 17.4 minus 70. You pulled a fast one on us, Mr. K. Yeah, it should be, but if I do that, then I should remember not to put the negative here. In other words, you go, well, how do you know? Well, I know that if I'm compressing the gas is going to do negative work. So I don't care how you write this, whether you write it with a negative or you do the final minus the initial. As long as you get negative for the answer, that's what matters. You see? So if you go like that and just write 17 minus 70, I'm okay with that. Okay. Oh, the other thing that we haven't asked even for the first portion is what's the heat into the gas during the isothermal state. We ask the work by the gas, but what's the heat into the gas? So then we use go back to here and say Q into gas is equal to what? Delta E of gas plus work by gas. During an isothermal expansion, what happens to the delta E? If the temperature does not change, delta E is 0. The Q into the gas is the work done by the gas, which is 34.53. So in other words, that allows me to go like this. A wiggly line, Q into gas is 34.53 kilojoules. In other words, the very reason the gas is expanding isothermally is because I am putting heat into that engine. How? Maybe it's an 1820s heat engine, coal, putting coal into the engine, burning it. You're burning the engine into a cylinder. You see, you gotta put heat into that gas. That's how you run any engine. And then the cylinder starts to expand. Gas expands isothermally, you see. So if it's isothermal, all the heat you put in goes into the gas doing work. None of it goes into changing the temperature. So now, how about the isobaric? What's the heat? It's gonna be heat out of the gas, right? You're gonna dump the heat. So then what's gonna happen? Go to the isobaric, heat into gas is delta E plus P delta V. Oh, we already have an equation for that. It's NCP delta T. Remember? NCP, where CP is the the molar specific heat. NCP delta T. So now that depends on what kind of gas we're using to run this engine, monatomic or diatomic or triatomic. During the isothermal, it didn't matter, you see? So if it's monatomic, then CP is gonna be what? So N is gonna be the number of moles. CP is gonna be for monatomic 5 halves. 5 halves times R. And then delta T is the temperature it has here minus the temperature it has here. Right? So it's gonna be 92.7 minus 373. Gotta keep track of all this, right? Final temperature minus the initial temperature. Diatomic CP, no, monatomic CP is 5 halves. Negative 46.6 kilojoules. Q into gas, negative 46.6 kilojoule. Well, that means you're dumping that heat back out to the atmosphere. So how would I write the line? It's coming out of the gas and you're dumping it into the atmosphere, 46.6 kilojoules. You see, so, you know, ooh, wait, it's weird.
Yeah.
Is that right?
Yes, negative.
But that's more heat than what you put in. It's weird for the gas to dump more heat than what you put in. Oh, you know what? Here, we're probably gonna have to put more heat in.
To increase the pressure.
Yeah. In order to go up, to increase the pressure back up at constant volume, we're gonna have to put more heat in. So you're burning coal at these two ends of the process, right? And then this one you're dumping. You can't dump more heat than what you're putting in. That doesn't make sense, you know? So, yeah, let's see. What else should we ask? We've got the work done by the gas. Oh, we need to ask the delta E of the gas, the change in energy of the gas, the delta E. Oh, you know what? We could do that by just simply doing, we already know the Q into the gas is negative 46. And then the work done by the gas is what? PDV is gonna be negative 18. Kilojoules. So this is the work done by the gas. This is the negative. This is the heat is negative, which means you're dumping it. This is the work done by the gas, which is the PDV. Where was that? Yeah, right here. And then now this goes to the other side, and then you can solve the delta E of the gas. So in each stage, essentially in each stage, I'm asking the Q into the gas, the delta E, and the work done. The delta E, the Q, and the work done. Delta E, Q, and work done, and all the pressure and temperature at each corner. So then the delta E is gonna be, this one goes over there, you add 18, and that gives you what? $27.9. Negative 27.94 kilojoules. Okay, now we're left with the last stage of the problem. The isovolumic. Going up. That one, you can't ask anything in terms of temperature because we know when it goes up, it should go up to the same temperature and it should go up to the same pressure that it began. So we already know that. So the only thing we can ask is, what's the work done by the gas? Well, work done by the gas in isovolumic is what? It's going up, so there's no area under the graph. So gas doesn't do any work in isovolumic. So work by gas is 0. Right? Last stage. Okay, so then what else you can ask? Q into gas is delta E of gas. Right? That's equal to what? NCV delta T. Okay, in other words, I'm gonna have to burn some coal to create energy and put it back into the gas. Q into gas is gonna be what? 8. What's the CV of a monatomic? 3/2 times 8.314. Delta T is what? Oh, it's gonna go back to 373, right?
It's the same.
373 minus,
92.7.
yeah. $27.96 kilojoules of heat into the gas. So you can say 27 right here. 27.9496 kilojoules. So I'm putting in about 28 kilojoules, 34 kilojoules, so roughly around 60 something kilojoules. And then I'm dumping 46. You see? Yeah. I'm putting in more heat than dumping. And then as a result, I'm doing work. So the last question we could ask is, what's the total work done by the gas during the whole cycle? What's the total energy change of the gas during the whole cycle? And what's the total heat input into the gas? A, B, C, D, E. What's the work total by gas? What's the heat